Hello and welcome everyone. My name is Alex Proskourin and this is our workshop on feature importance analysis. So this workshop will apply MDI, MDA, CFI, model fingerprints, SHAP and line techniques in order to analyze features in breast cancer dataset. So this is quite well-known standard dataset which is used to play around with classification type of algorithms. So let's start with imports. So as you can see here, we'll use quite well-known imports and libraries in data science, like sklearn, pandas, numpy. Here we use Shapley SHAP package for Shapley value feature importance. We use line package for line feature importance, and of course we'll use ML Finlab. So let's start our workshop. So on the first step, we will load breast cancer dataset and execute this row, which is quite important. So we will sort our features in alphabetical order by applying np-unique of x columns, because np-unique function not only deletes duplicates, but also sorts the output in alphabetical order. Why it is important? Because as we have discussed in our modeling lecture, if you would like to set your random state in random forest classifier, which will be used in this notebook, you can set random state only for choosing the way random sample subset are fit into our weak estimators, like decision trees. But there is a problem with random forest, that it also uses the random feature subset, and there is no way to set up random state for random feature subset selection. So how we can fix this random state is by sorting our columns in alphabetical order. So in this case, we are always sure that our columns are sorted alphabetically, and this is a tricky way to fix random state for random forest classifier, and you can reproduce your results in the future. So let's load our data set and take a look at that. So as you can see, it consists of 30 columns with it consists of 30 columns which describe breast parameters like area error, compactness error, concavity error, etc. So the purpose of this notebook is to understand what kind of features have the, bigger impact on our model results. We'll use a standard k-fold scheme with number of splits equal to 5. And let's start with model setup. So in our modeling lecture series, we have discussed how to a tricky way to set up Bayesian classifier, which works on top of random forest classifier. So let's see how it is done. So what we do here is we set up a base estimator of random forest classifier with bootstrap equal to false, because bootstrap will be done by our Bayesian classifier with number of estimators equal to 1. So have only one estimator and criterion equal to entropy. And we will set up Bayesian classifier on top of our random forest classifier with number of estimators equal to 100, max features being equal to 1, and random state equal to 42. So in this case, we fix our random state value. So let's see what kind of accuracy and F1 score the model shows on our data set. So as you can see here, the scores are quite high with relatively low standard deviation, and we're quite sure that the model has captured the right pattern. So now let's analyze what kind of features are responsible for this high score. So first we will fit our Bayesian classifier. As you can see, we fit it on top of random forest classifier with bootstrap equal to false, criterion equal to entropy, and estimators equal to 1. So let's start with well-known mean decrease impurity feature importance. So how do we use that? So we use ML Finlab's feature importance module mean decrease impurity. So what are the input of this function? The input is your train model, which is important. You need to train your model before using MDI feature importance. We pass feature names for beautiful representation in pandas data frame, and here we can see cluster subsets. We'll discuss later in this workshop what this parameter refers to, but if you remember from our lecture series, cluster subsets are used if you would like to use clustered MDI feature importance. So we can take a mean value of MDI, standard deviation, take their sum and sort in descending order by MDI. So the MDI feature importance shows that worst perimeter, worst radius, worst area, mean concave points, and mean area features are one of the most important. So actually the shape of your of the breast parameters are one of the important of not breast parameters but rather the so actually the shape are important parameters, right? So let's go deeper and find what MDA feature importance shows us. So MDA feature importance is out of sample feature importance function, and it takes several inputs such as your model, your X, your Y, your cross-validation scheme, which is k-fold cross-validation, your cluster subsets if you would like to use clustered feature importance. As we have discussed in our modeling section, in financial machine learning, you can pass specific train sample weights such as returns based or time based or t-values based, and you can also pass sample weights to weight your scoring functions, because as we have discussed earlier, various samples have different impact on your PNL, and that's why you need to pass sample weights, score weights to get a better modeling of financial logics in your data set. What we can see here that it also takes scoring function as input with the default value of log loss function. So once more, as we have discussed, mean decrease accuracy is called MDA, but actually you can pass any function to mean decrease accuracy. If you pass a function such as log loss, which requires probabilities to measure the value of function, you should also specify require proba equal to true. As we use in our data set F1 score, which does not require probabilities as input to a function, require proba equals to false. And the final parameter is number of repeats. So as we have discussed in our lecture, there is a wonderful paper by Ernie Chan in Journal of Financial Data Science, which says that it is a good practice to generate MDA feature importance with various random states and to average those results, which yields much more stable feature importance values. So here we will use MDA with 2 repeats. So we'll do MDA feature importances with 2 random states, and then we'll average the results. But the common guideline is to use at least 20 repeats in MDA feature importance. So we will also generate mean plus standard deviation column and sort that in descending order. So let's take a look. So here we can see that actually some of the features which were already present in MDI, such as worst radius, perimeter based features, are quite important. But what we can see is that there is a feature which is called worst texture, which is actually the top feature found by MDA. But if we take a look at the worst texture feature in MDI, it is quite far away in our feature importance. And this is one of the reasons why usually MDI is more reliable, because it uses your out of sample score to measure the importance of features. And that's actually what we are interested in when we try to understand what kind of factors are the most important. So now let's go into clustered feature importance. So as we all know, and we have discussed in our lecture series, that we would like to group our features to sort the problem of substitution effect, and that's how cluster feature importance is very applicable. One also small note, as you can see, some of the features like mean texture show negative results just because actually worst texture, they are quite correlated with worst texture. And that's why they have negative results in MDA. But our logic tells us that actually this feature should be also important. And this is one of the problems with MDI and MDA because they do not take into account substitution effect. And that's where cluster feature importance comes in action. So let's take a look how we apply cluster feature importance. So as we have discussed, cluster feature importance, on the first step, we need to understand how to group our features into clusters. So let's take a look what are the different ways to do that. So we have 30 features. What we can actually do is to apply MLFinLab's function, which is MLFinLab clustering get feature clusters, which takes several inputs. So the first one is our data frame of features. The second one is the dependence matrix, which can be either linear for linear Pearson correlation, information variation, mutual information, or distance correlation. It also takes your distance matrix, which can be either angular, squared angular, or absolute angular. What I have seen from my practice, angular is more than enough to get a good representation of your features on datagram. It also takes a linkage method as input parameter, which can be either word, single. It can be also, let's take a look at the documentation, single, word, complete, average, or weighted, and centroid. So this is the way how agglomerative clustering bisects our features into clusters. And the final feature value is number of clusters. So actually finding number of clusters is quite is not that easy because you need to either specify it by your own, so try to understand what kind of clusters, or to come up with some kind of quantitative procedure which does it for you. What you can actually, how you can actually find the optimal number of clusters is to call MLFinLab clustering get ONC clusters. So this procedure takes your correlation matrix of features as input and finds the optimal number of clusters using k-means clustering algorithm. So let's take a look what this function does and just go further in our notebook while it is running. So as we have discussed, so actually it has already finished its run. We can see that the optimal number of clusters function generated several clusters. And the number of clusters is 1, 2, 3, 4, 5, and 6. So the optimal number of clusters by ONC function, which uses k-means clustering, is 6. And these are our clusters. So let's see if we set the optimal number of clusters to agglomerative clustering and see what kind of clusters we get. So here we use linear function as input. The distance matrix is angular, linkage method is word, and number of clusters is 6. So if we see here, the clusters which were generated out of hierarchical clustering are a bit different. So for example, k-means created a separate cluster of mean texture and worst texture. The agglomerative clustering technique, actually it made the same cluster for mean texture and worst texture. Okay, so actually these are good news for us because k-means clustering and agglomerative clustering generated the same clusters by each algorithm. So let's take a look at these clusters. So the first cluster is actually related to the geometrical properties, such as area, mean error, perimeter, radius, worst area, radius error, etc. The second cluster is more about compactness and concavity. So we can see that we have features like mean concavity, concave points, compactness. Yeah. The third one are more about your texture, like fractal dimension, smoothness, symmetry, fractal dimension, worst smoothness, worst symmetry. This is a texture-based cluster. And we also see that we have an error-based cluster and compactness error cluster. So sometimes you can either use optimal number of clusters of algorithm to find the number of clusters, but what you can actually do is to take a look at the dendrogram of your features, which is created by agglomerative clustering algorithm, and get an intuition of what kind of clusters can you get for your features. So let's take a look how we can do that. So this function creates number of clusters when you specify the dependence matrix, your distance matrix, and your linkage method by agglomerative clustering, but you need to specify the expected number of clusters. So how we can plot the dendrogram is to use linkage function from SciPy. The method is single. So let's use, this is the linkage method. So let's use word linkage method and use linkage function on top of correlation matrix. So here it corresponds to dependence matrix being equal to linear, and plot the datagram of our features. So as we can see now, this function plots a beautiful dendrogram which groups features using agglomerative clustering technique. So actually, we can see that some of the clusters like mean perimeter, mean area, mean radius, worst perimeter, worst area, worst radius, create those clusters which were generated by optimal number of clusters and agglomerative clustering technique. So by using the dendrogram, you can either understand the number of clusters. So here we can see 1, 2, 3, 4, 5, 6. So by taking a look at the shape of dendrogram, you can actually also define the number of clusters and also use your domain knowledge to understand how you should cluster your data sets. So let's take a look at our clusters. You can also create them by taking a look at dendrogram and to create them manually by creating this type of data structure. So this is array of arrays. And if we find the lengths of clusters, it is 6, right? So now let's build MDI and MDA clustered feature importances and see what comes here. So we can see that we can apply a mean decrease in purity, and this is important note because in MLFinLab we don't have a separate function for clustered feature importance, but you rather use clustered subsets with clusters being equal to your cluster specified data structure instead of using a separate function. So if you would like to use a clustered feature importance, just use mean decrease in purity or mean decrease accuracy with cluster subsets equal to clusters. So now let's take a look at your clusters. And what you can see here is that actually the shape of our feature importance data frame has changed. So if we take a look here, we can see that for this cluster, which is related to the shape of to like shape-based features, they are the top features, and this is quite logical to us because these features describe the shape of like describe the shape which is important to define either it is a breast cancer or not. So the second cluster, so as you can see here, all these features have the same value of feature importance because this technique is clustered based rather than individual features based. So all these features, because they are in the same cluster, have the same feature importance value. So after that, we have the concavity related features. After that, we have smoothness related features. At the end, we can see that the features which are related to symmetry, smoothness, and texture error are not informative at all. But it's important even to filter out features because you don't want to put non-informative features in the data frame. So by deleting non-informative features, various papers show, and also Ernest Chan paper in Journal of Financial Data Science show that by deleting uninformative features from your data set increases your cross-validation score. So now let's take a look at MDA feature importance values. So we can also see that, so here, once more, we use mean decrease accuracy function. We put clustered subsets to as input to create clustered feature importance. We don't use sample weights here in our data set problem. We use number of repeats equal to 2, just not to wait too long for function to calculate. But a good guideline is to use at least 20. Require proba equals to false, and we use F1 score. So now what you can also see is that worst radius and shape related features are extremely important. So just take a look at the significance of this cluster. So it is very big. So like with an average score of F1 score of 0.9, the cluster importance with mean plus STD is 0.6. So like it is extremely important. Also, concavity related features are important for us. And what we can see is that fractal dimension, concavity error, compactness error, and concave points error are informative features. So what we can see that actually top clusters, such as shape-related clusters and concavity-related clusters, and texture-related clusters. So this is, as you can see, concavity-related cluster, which have the same feature importance, and texture-related clusters. They are the most important in both. So like shape-related cluster and concavity-related cluster are both most important in MDI and MDA. So that's one of the advantages of cluster feature importance, because it is extremely stable. So usually you will see that your informative clusters are both at the top of MDI and MDA values when you group them on cluster-based level. So in this case, you can understand and get a better intuition what kind of information is important for your model and how to maybe generate more features. Because instead of analyzing individual features, you analyze types of information which you put into your data frame, into your model. So for example, here we put the shape-related features, compactness-related features, texture-related features, and analyze not individual features important, but rather the importance of the information piece which you put into your model. So now let's take a look at model fingerprints algorithm. So how do we use that? We use still ML, feature important, classification model fingerprint, and we just need to fit our algorithm. So we use our classifier, we specify X. So what is the pairwise combinations value? Because the number of pairwise combinations of 30 features is relatively high, imagine that you have 700 features. So the number of combinations of 700 features of 2 is huge. So if you put all possible pairwise combinations to test for model fingerprints algorithm, your algorithm will run for ages. So that's why in ML FinLab, you need to specify what kind of combinations you would like to test for pairwise effect. So here, we don't want to test any pairwise combinations, but still the user can specify his own combinations. And the final one is number of values. So let's take a look at function documentation. So here I have model, I have X, I have number of values, and pairwise combinations. So pairwise combination is a list of tuples such as features I, features J to test the pairwise effect. So if, for example, you would like to test for mean texture and mean radius, you should pass this this data structure into your model fingerprints algorithm. And the final value is number of values. So actually, how model fingerprints works? So it loops through the all possible values of your features, and it changes the feature value, and analyzes the way the prediction of our model changed. So for example, let's say, for example, the feature value ranges from -100 to 100. So it will take all data points, all features values, starting from -100 to 100, and analyze how your predictions change. So it will analyze what is the prediction value for feature being equal to -100. So what is the prediction value for minus 99 up till 100. In this case, the number of computations becomes also quite large and quite big, because let's say, for example, have 700 features and the number of your samples is 7,000. So it will generate so many predictions, and the algorithm will take so much time to compute. So what number of values says is actually the number of quantiles which we test our features on. So instead of using each value, you can actually go with some kind of step, like with some kind of quantile. So in this case, number of values means that you will take every 20th value of your feature to test for your model fingerprint. And why it is quite good parameter, because you decrease the number of computations massively, but usually the performance and the results of your algorithm don't change that much. So when we have fit our model fingerprints algorithm, you can just call function which is called getEffects. So this function yields a tuple of linear, nonlinear, and pairwise interactions effect. But as our pairwise combinations are equal to none, it will return empty tuple. So there is no way to return that. So let's take a look at linear effect in our model fingerprints algorithm. So as you can see, linear effect is a dictionary and has two keys. The first one is raw, and the second one is norm. So the raw linear effect is the raw value of your linear effect, which is calculated as discussed in paper. But usually, you would, instead of analyzing raw values, you would like to rank your features based on these raw values. So to find a normalized and relative effect strengths. So you don't need usually to see the linear effect of 0.999 or 0.001. But you would rather would like to understand what kind of feature has the highest linear effect and highest nonlinear effect. So in this case, in MLFinLab, we have normalized our raw effects and put them into into normalized dictionary. So if you take a look at linear and pass norm here, you can see that actually worst radius has quite big nonlinear effect. What we can also see here that, for example, worst area has very high linear effect. Worst concave points has extremely high linear effect. So you can analyze that values, these values, to understand what kind of linear effects are generated by features. So let's take a look at nonlinear effect. So it has the same API and the same structure as linear effect. So here we see that area error has quite big nonlinear effect. We can also see that worst radius, worst perimeter and worst area have very high nonlinear effect. And for example, radius error has a very high nonlinear effect. So this algorithm actually tells us what kind of features may impact dramatically, especially when you analyze nonlinear effect, may impact dramatically the value of our the value of our predictions, which is extremely important if, for example, in financial machine learning, you would like to predict tail events, because there are several indicators for which a very small change in feature value may lead to huge price swings and will modify the prediction of your algorithm extremely seriously. So now let's move deeper into Shapley feature importance. So here, there is a small note. In Shapley feature importance, we use we use tree Shapley explainer. So there are various ways to explain Shapley feature importance. And if we use tree-based models, the fastest way is to use tree explainer. But also in Shapley feature importance, we have additive explainer, deep explainer. We also have graded explainer, kernel explainer, linear explainer for linear models, partition, permutation, etc. But for tree type of models, Shapley package created a great explainer, which is called tree explainer, which is fast and it is designed specifically for tree-based models. But there is a small note here, is that tree-based explainer in Shapley feature importance can only work with either gradient boosted trees or random forest classifier. So tree explainer cannot work with bagging classifier. So that's why we'll retrain our classification model and use it as input to our Shapley feature explainer. So it takes your trained model as input, and then you can create Shapley feature value feature importance values. So actually, Shapley feature importance values, as we have discussed in our lecture, can be also used as a proxy to your feature importance. And Shapley generates two types of Shapley values. So the first one, which were used to predict zero class values, and the second one, which are used to predict like label equal to one labels. So if you use a regression setting, you won't have that kind of structure because in this case you have only one Shapley values for all features. But in classification setting you have zero class Shapley feature importance and one class Shapley feature importance. So let's create the zero class feature importance values based on Shapley and class 1 feature importance. As we can see here, we use the absolute values and we take the mean value of Shapley feature importance and sort them. So what we can see here is that actual worst perimeter, worst concave points, worst area, worst radius. So we still see that actually like the same set of features relatively are present in all feature importance functions, which usually means that the algorithm has captured the right pattern because the informative factors are pretty much the same. So what we can see here is that actually the same feature importance values are present for class 1 feature importance. So it has worst perimeter, worst concave points, worst symmetry, worst radius, area error. So they are absolutely the same. So as you can see here, the shape values for the first class look like a list of lists. And for example, if you take a look at the zero value, so this is the Shapley value for zero sample, it should equal to 30, which corresponds to the length of our features. So these are the Shapley values for all our features. So let's use extremely helpful functions from Shapley values to get a better understanding of how we can um, get a better understanding of how the model will predict the feature values. So let's take a look and sort our features based on MDA score and build dependence plots. So what dependence plot shows us is how feature value will affect the prediction of our classifier model by by building this dependence plot, we can take a look at that. So how it is done? So first we generate sorted columns lists, and what we do, we use Shapley dependence plot function, which uses our column as input. Would like to predict the probability of zero class of class 1. So by specifying 0, you can build Shapley dependence plot for zero class. Our features matrix is X, show equals to false, because like in my practice I really like to plot grid on top of that, so that's why I put show equal to false. Then we use PLT grid equal to true and use PLT show. And this is like very good function, which is also useful because sometimes your feature values can be quite spread. It is quite difficult to plot them on one plot because it has quite high standard deviation. So that's why dependence plots have quite cool parameters to crop your plot by specifying the quantiles which you would like to plot on in your data set. So here we'll plot the dependence plots for values of features starting from first percentile up till 99th percentile, which actually covers almost all feature values, but it will still crop some outliers for our features. So let's plot the dependence plot for our features and see what comes here. So what we see here are so-called dependence plots. So what it says, so here it shows the values of your features. So this is the worst radius feature values. It also shows with heat plot. So here you can see dots. This is the feature which interacts with worst radius in the most cases. That's the opinion of Shapley algorithm. And here we can see the Shapley values for predicting positive class. So what we can see from this plot is that lower radius, worst radius values will increase the probability that class value equals to 1. And high probability values, high worst radius values will decrease the probability. So if, for example, we plot the 0 class value, you can see that actually your picture reverts because higher worst radius values will increase the probability of 0 class and of course decrease the probability of class 1. So let's plot 1 class. So in this way, you can actually understand how your model thinks and what kind of patterns generated your model. And based on that, you can build new economic theories. You can understand how the feature value will impact the prediction of your model. So what we can also see here that lower worst area points also yield higher prediction of class 1, worst perimeter, mean area, mean radius. Here we can see nonlinear dependence for worst concave points, worst texture, cavity error, backness error, area error. Just to make sure. Okay, so we have the array of 0 and 1, so that's okay. So that's actually the kind of pattern which was captured by our model. So here, these are dependence plots, which are extremely applicable if you would like to get a better understanding of what kind of pattern which was captured by your model. So now let's build summary plot. So summary plot also builds these nice plots, which are, as you can see, so summary plot sorts your features in descending order of Shapley feature importance and shows the output of feature value on the model output. So what we can see here is that low values, so the feature value is low, lower values of your worst perimeter lead to higher probabilities of class 1. So here, as you can see, you have input the probability of class 1. So if we make it this one, you can see that the high values increase the probability of class 0. And summary plot is summary plot is just a short version, I would say, of dependence plot if you like to quickly analyze how your features impact the probability of 0 label or 1 label. And the final function in Shapley feature importance is a called force plot. So let's say, for example, that your model has predicted the probability of class being equal to 1 with a very high probability of 90%. You would actually like to understand why did the model predicted these kind of probabilities in this particular case. And that's actually what your force plot does. So let's take a look at index 19. So the model has predicted, so the value of label is 1. So what we do is we create a force plot, and we like to understand how our features voted for class prediction of 1. So what we do is because Shapley uses a JavaScript network framework, we use shape in EGS. We also use shape force plot, and so we measure the force plot. So how Shapley works is it has, I would say, two um, equilibrium levels for 0 class and 1 class, and our features start to vote to move the prediction out of equilibrium level. And the equilibrium level is actually explainer expected value. So this is the equilibrium value for 0 class and for 1 class. So we would like to build the force plot for features which voted for the probability of 1. So we use explainer expected value 1, Shapley values 1, and features be equal to x. So it generates a great plot which shows how our features voted for each sample. So if you, for example, sort them by original sample ordering, you can take a look that, for example, so in this case, we generated the probability of a class being equal to 0.08, and actually all features like area error, mean concave points, worst area, worst perimeter, worst concave points voted, like were responsible for voting for 0 class, so like for decreasing the probability of 1, and only worst texture label was responsible for voting for the probability of 1. But let's say, for example, here, the output value of our function was 1. So we have predicted with a very high of probability that the value of label is 1, and worst perimeter, worst concave points, and worst radius features were responsible for that kind of prediction. Sometimes our features start to, they have a rivalry between them, because here we have predicted with high probability the feature value, the sample value is 1, but on the one hand, mean concave points, worst texture, mean texture, texture error voted for the class being equal to 1 because they are highlighted with red. But worst radius and worst perimeter features voted for 0. But at the end, our class 1 features won, and the model predicted 0. Like the Shapley values, the Shapley value is 0.94 for this feature. This graph is quite great to understand the explanations on many samples, but we can take a look at the sample which we may be interested in by building a separate force plot. So here we choose the instance of xi log of index. So as we have discussed, we are interested in index 19, right? So if you take a look, this is the index 19. We choose this instance. We choose the Shapley values for this particular instance, and we would like to predict the probability of class 1 by showing the explainer expected value, Shapley features of class 1, and we pass chosen instance into this plot. Okay, so we have predicted the value of 1. So with a very high probability, the model predicted that class value is 1. And what are the features responsible for that? So the worst perimeter being equal to 99 and 7 voted massively for feature value being equal to 1. Mean concave points was the second one responsible for that. So it sorts the way the impact of features on model output into descending order, so you can see those features which were the most responsible for your prediction. So if we change the output value to 0, we can see that the value of 0 is equal to the probability of label 0 is equal to 0, right? And worst perimeter and mean concave points and worst area were just dragging the probability of 0. So these features were voting for 1 massively, and of course they will decrease the probability of 0 massively because they vote for 1. So as you can see here, worst perimeter and mean concave points. And for 1, we have worst perimeter and mean concave points. So Shapley values is extremely applicable and useful package if you'd like to get a better understanding of what kind of patterns were catched by your model, and actually how to understand how your features voted in particular sample. And the final feature importance technique is so-called line. So this is also quite similar to Shapley feature importance because it decomposes the prediction of our model and shows how the features voted for the value. And it is a great addition to our Shapley force plot and dependence plots. So let's take a look. So line also needs a tabular explainer. So it's line tabular explainer. We need to pass values of x. It is quite important. We need to pass the numpy array into line explainer. So if we take away values, so we take x values. So this is our array, and we need to pass feature names. So the line will do it, will do all the work for you. So if we just pass our matrix of x as pandas data frame, line explainer would generate error. So let's pass values. We created values of, we have created the explainer, and now we create the instance. So now we would like to understand how line thinks our features voted for index of 19. So what we pass into our line feature importance function, we pass x.ilog index values. So as you can see here, we still pass numpy array. We're here also pass the probability function. So for our particular classifier, we specify that we would like to use the prediction of probability by our trained random forest classifier, and number of features being equal to 10 mean that we would like to analyze only top 10 features which were responsible for the prediction. So now we generate the explanation and show it our notebook. Okay, so the feature value is 1, and what the line actually thinks is that mean texture, worst texture, area error were the most responsible features for predicting the 1 value. And here we can see also that in our table, mean texture, worst texture, because they are less than some threshold values, and Lime already, so that's how Lime analyzes it. So it analyzes various thresholds and builds a proxy to a dependence plots by Shapley values, and we can see that the mean texture is less than 16, 17, worst texture, area error in some kind of range, and these are the most responsible features for predicting 1. Mean concave and worst concave were actually voting for 0, so that's how Line thinks in terms of this prediction. Worst concavity was voting for 1, etc. So Lime is a different approach comparing to Shapley when you would like to decompose the prediction of your model and understand what were the drivers of that particular prediction. So in this notebook, we have discussed how to use MDI, MDA, clustered MDI, clustered MDA to measure the feature importance values. We have also understood how to decompose the effects of our features using model fingerprints. And at the end of the workshop, we have analyzed how Shapley and Lime packages are used to either analyze the feature importance, the raw feature importance, how to understand what kind of patterns were catched, and how to decompose the prediction of your model on feature level, and understand what are the key drivers and the reason for that particular prediction. So in this case, machine learning is no longer a black box, but rather a white box, because you have a clear understanding on how features detected your patterns and how your model, how not features, how model detected the pattern and how your model generates predictions.